It's an honor to be here to celebrate with everyone Michael Fogelius' birthday. I first remember Michael from when he was a postdoc at Courant and I was a beginning graduate student. I remember being at your first lecture there and then getting to know you personally over the years, visiting Rutgers, and then more recently as a collaborator. So I'll be speaking on waves and microstructures. There'll be two topics in my talk. First is scattering and dispersive wave properties of microstructures and a kind of breakdown of homogenization that we'll see how to correct. That's joint work with Vincent Duchesne, and who's now at Hennenfent, and Iva Vukasevic, who's a graduate student at Columbia. Also, Vincent will speak on related work on Thursday. The second part of my talk concerns waves in regular and deformed honeycomb structures, and that's joint work with Charlie Pfefferman. Okay. So the first topic, so in scattering and dispersive properties, so the motivation will be from, say, the Helmholtz equation. So imagine a compactly supported but microstructured, a layered media, some highly oscillatory medium. Okay, so time harmonic solutions satisfy the Helmholtz equation. The wave number k is 2 pi over lambda. Lambda is the wavelength. And as waves propagate in the structure, they'll either spread out laterally in the x direction, or possibly get localized, and they'll also propagate in this vertical direction, in the z direction. So for example, if I wanted to look for guided modes, they would be solutions of the form of the separation of variables form, e to the I k z, f of x, where f could be written as solving a Schrodinger equation, where the potential is obtained from the refractive index, n of x, like this. And I'll be looking at microstructures, so these are going to be things that are functions of, a microstructure for me will be a potential for the Schrodinger equation, which is localized in this slow variable x, and say periodic, or it could even be almost periodic or quasi-periodic in the second variable, x over epsilon, which will be denoted by y. Okay. So here's the problem. It's an eigenvalue equation with frequency k squared. And we have a Schrodinger operator, Laplacian plus q of x and x over epsilon. Or more generally, Vincent will talk about the case where one has Laplacian plus a periodic function of x, globally periodic in x, and then this defect or microstructure, which is compactly supported in the slow variable and rapidly varying in the in the second variable. And think of it. Here's a toy example. This is supposed to be a toy model of a microstructure. Some very large number times something oscillatory times something compactly supported. Okay. So we're interested in things like that, or superpositions of them, general things like that. We ask, what are the scattering and localization properties for such potentials? And the claim is that, these are going to be mean zero with respect to the fast variable. And the claim is that although you can homogenize this trivially just by averaging the potential and getting then just the Laplacian, the key properties are not modeled well by this homogenized operator. Okay. So the first result then with Vincent and Eva is that this problem exhibits something called an edge bifurcation. Let me explain what that is. So we assume that we have a high contrast microstructure, so something which is not small in L, bounded, this could be large in L infinity, rapidly oscillatory and spatially localized. Doesn't have to be compactly supported, just sufficient decay as the first variable x goes to infinity. And we assume that it's periodic, or, well, it could even be almost periodic. There could be infinitely many frequencies. They can be incommensurate. They should just be a nice family of frequencies. And by nice, that means that, it has to be mean zero, so none of these lambda j's should be zero. And secondly, they shouldn't cluster. Okay, so they shouldn't bunch up. Lambda j minus lambda k, can't go to zero as j and k go to infinity. Okay. If that happens, then you have sort of small divisor type issues. The conclusion is that this operator Although its average is 0, and homogenization would predict just no bound states, this actually does have it always has a bound state. And here's its expansion. It's a bound state of size epsilon to the 4, minus epsilon to the 4 times some coefficient. The more detailed statement is that this operator, Schrodinger operator HQ epsilon, is very well modeled by this effective operator with an effective potential. The effective potential is a small potential of size epsilon squared. Notice that it's always negative. It's a sum of minus the sum of squares. So even though its mean 0, the effective potential is always a potential well. Okay. Okay. Now, there are implications for the time dynamics, so it makes sense to compare the time evolution of the free problem, that's the homogenized time evolution, with the full problem. So we, just as a review, so if you have the free Schrodinger equation, the solution is explicitly given by the convolution of the initial condition with a complex Gaussian. In one space dimension, the rate is 1 over t to the 1/2. That's the dispersion rate. So this is the L1, L infinity estimate. And we can ask, well, what happens for the full evolution with potential Q epsilon? And for this, well, what we have to do first is project out the bound state, because we see that there is an eigenstate that gets kicked out of the continuous spectrum. So let's project that out. That's a one-dimensional projection. And then we expect the rest to disperse. And so this is the dispersive estimate that one gets. One has a dispersive estimate with a multi-scale structure. That if you localize, so this isn't quite L1 and L infinity, but so essentially this is saying if we look on a compact set, the decay rate is free for a while, but then it picks up this enhanced dispersion on a time scale of order 1 over epsilon to the 4th, if the initial condition is sufficiently localized. Okay, this is we can think of this as a multi-scale dispersive estimate. So where does this all come from? Well, the heart of the matter is the transmission coefficient associated with the structure. So let me remark that, well, I'll define the transmission coefficient in a moment, but poles of the transmission coefficient, this is some function which is can be extended to the complex plane if the potential is sufficiently localized, and, well, always into the upper half plane, but, and if the poles in the upper half plane correspond to eigenvalues. Poles actually on the imaginary axis correspond to eigenvalues of the Schrodinger operator. You just have to square them, and you get eigenvalues. So that's one. That's related to theorem 1, and theorem 2. Well, that has to do with the time dynamics, and using the spectral representation, you can write the evolution operator after projecting out the bound state as a Fourier integral. And if you look at the spectral measure, okay, that's dk, d mu of k is this measure dk, Lebesgue measure, times the transmission coefficient squared. And so here again, the transmission coefficient is going to govern via stationary phase type ideas the time evolution. That's used to prove theorem 2. So we want to understand the transmission coefficient. And we want to understand it for small epsilon as the potential gets more and more oscillatory. And so the original motivation for this investigation was understanding homogenization limit of scattering quantities like transmission coefficients, reflection, scattering resonances. And I was motivated particularly by work of Santos and Fulgelius, Moscow and Fulgelius. These were influential papers. There have been quite a number since then, where they looked at homogenization of eigenvalues for self-adjoint problems like the Dirichlet problem on a bounded domain, Neumann, etc. Okay. There was great interest, actually. There is great interest in the optical sciences, because very often we are interested in propagating waves through microstructures, and scattering type quantities are really the things of greatest interest for that. Okay, so let's now look at the scattering problem. So we want to think about scattering experiments, and a scattering experiment works as follows. We look at an incoming plane wave, e to the ikx, and some of it gets reflected and some of it gets transmitted. So here is a plane wave, and what results is a distorted plane wave. If there were no potential, what's drawn here is like a potential barrier, but just think of this as your microstructure if you want. So since it's spatially localized, it'll be free to sufficiently far to the left and sufficiently far to the right, so you get reflection and transmission from the left into the right, and then associated with these incoming conditions at minus infinity or plus infinity are the so-called distorted plane waves. And distorted plane waves satisfy an integral equation. This is just the free Green's function. In one dimension, it's essentially e to the ik x minus x prime. And one could define the Yost solutions, which, well, I guess let's. Oh yeah, the Yost solutions are defined by just factoring out the transmission coefficient. Those turn out to be better objects actually to look at. Okay, and. So, all right, the question is, well, how do these transmission coefficients vary as epsilon tends to 0? Okay. Now, if we look at the problem where Q is, if we just average the problem, okay, then we just get a problem with transmission coefficient, which is identically 1, right? If we send in a plane wave, it's just going to remain a plane wave coming from the left or from the right. Transmission coefficient is equal to 1. And so this investigation actually began with, at first, Eva looking at numerically at the behavior of the transmission coefficient as epsilon goes to 0 for some compactly supported potential like that toy model. And what you see is that for smaller and smaller epsilon, these are the transmission curves. So this is for a fixed epsilon, this is for a smaller fixed epsilon, and yet smaller. Well, as k gets large, as k goes to infinity, well, you expect nearly all the energy to transmit through the potential. So it's not surprising that these all go to 1. But then what you see is that they all head down to 0 at zero energy. Okay? So this is a property of the Schrodinger equation. It's not a property of Helmholtz equation, Maxwell's equation, but it is of the Schrodinger equation in 1 dimension and something analogous in 2 dimensions. So there's a non-uniform convergence of these transmission coefficients to the homogenized one. So if I'm standing at an energy which is away from 0, then clearly you see nice convergence to the homogenized transmission coefficient, but that convergence is non-uniform. And that's not only a technical matter. This localization phenomena that one sees, this edge bifurcation, the bound state, is intimately connected to this non-uniform convergence. So the theorem is that, well, stated very roughly, is that as epsilon goes to 0, the behavior H epsilon or HQ epsilon behaves is well modeled by this effective potential, okay? Potential well. More precisely, if one blows up a neighborhood of low energy, then one sees that there's a universal scaled limit for the transmission coefficient. It approaches a scaled limit which we call T star of kappa. So here we're blowing up a neighborhood of k equal to 0. T star of kappa is this function, some universal limit, and it depends on a single parameter, namely the integral of the effective potential. Well, you see over here that there's a pole in the upper half plane. The effect, that lambda effective, that's actually the negative of the effective potential. This is a positive quantity, so the pole is always in the upper half plane, and so the bound state corresponds to the square of that once you undo the scaling, and that's where once you square this pole in the upper half plane, you get the bound state that was asserted. So let's look at this for a moment. You see, this looks like kappa squared. So in the unscaled variables, this will look like k squared over something that is regular as k goes to 0. And let me just go back briefly to this form. So now think of this as having an extra, for low energy, this has a factor of k squared now, because this is, So if and then so you could see from stationary phase that you'll get the t to the 3 halves, the enhanced dispersion coming from that. Okay, so what's the idea? The idea is we would like to get a good approximation for TQ epsilon. We would like a uniform estimate on the difference between TQ epsilon and some sigma epsilon, which we would like to be the effective potential. If I replace sigma epsilon, that unknown effective potential, just by 0, the homogenized one, this difference is not uniformly small. It is small away from 0 energy, but it is not uniformly small. So the idea is then to look at a resolvent type identity. We look at this. This is related to resolvent identities. You look at the reciprocals of the transmission coefficients. So this is a general identity. If I have two potentials, V and sigma, and I write down their transmission coefficients, I can represent their difference of their reciprocals as an integral like this, where these are oscillatory functions called the Yost solutions you saw in a previous slide. So there's the difference, V minus sigma, V sigma. And then these are e to the I ky type objects. This is an oscillatory integral. Okay. Okay. And one can show that this difference, after lots of integration by parts, these are oscillatory integrals, you want to extract the dominant behavior, you obtain that this difference can be expressed in terms of oscillatory terms and non-oscillatory terms. The oscillatory terms are non-resonant, those will oscillate to 0, and then there are non-oscillatory terms which keep the difference from going to 0, and we remove those terms by an appropriate choice of sigma. We choose sigma so as to kill the non-oscillatory terms. It's like a normal form calculation. Okay, and then we're able to get a uniform estimate. And so the sigma, which does that job, is the effective potential that we wrote down earlier, and it's always an effective potential well. Okay, so that's that. Okay. Okay, so the next part of my talk is on honeycomb structures, a joint work with Charlie Pfefferman. So we're interested in the wave properties of the Schrodinger equation, or the nonlinear Schrodinger Gross-Pitaevsky equation, for a very special class of potentials, which we call honeycomb lattice potentials. So first, let's start with the honeycomb period, the period lattice, the basic period lattice. So this is a triangular lattice of equilateral triangles. We take a constant A, which you could think of it, just take it to be 1 in this talk, which is the lattice constant. So this is the distance between sites, and then take 2 vectors, V1 and V2, these special vectors. These will generate a lattice. If I look at integer linear combinations of V1 and V2, I get a bunch of points in the plane, and you could connect them so you have equilateral triangles. Now, to get the honeycomb structure, what you do is you take 2 points, often denoted A and B, as base points, one at the origin, and then a point B, which is situated interior to the basic period parallelogram that's spanned by V1 and V2. So you take these 2 points, and then you look at the lattice with A and B as their base points. So you just take this triangular lattice emerging from A, and a second triangular lattice emerging from B. And the union of those 2 triangular lattices is called the honeycomb structure. Okay. So a honeycomb structure is not mathematically a lattice. These are individual objects or lattices. Those lattices like lambda h are called Bravais lattices in the physics literature. This is sometimes called a multilattice. So that's a piece of the honeycomb structure. The A points, the part of the A lattice, are drawn in blue, and are the blue dots, and the B lattice is the circles, and here are the basic, the generating basis vectors for the triangular lattice V1 and V2. So now let's say what a honeycomb lattice potential is. So for us, a honeycomb lattice potential is going to be a smooth function. One could relax this hypothesis, the regularity hypothesis, considerably. So let's just take a smooth function with the following property. After a centering of this function, v of x, the following will hold. So first, it's periodic with respect to the basic period vectors, basic triangular lattice, lambda sub h. It should be even. This is sometimes called inversion symmetry with respect to x0, the centering. And then v tilde is R invariant, which means that you just take, if you evaluate the potential at a point x, and then you rotate by 120 degrees, you get back the same potential. So this is a special class of periodic potentials, periodic functions, and so they'll have special Fourier series, and that Fourier series, that special structure is exploited throughout. So some examples. So the best known example is graphene, which is a two-dimensional honeycomb arrangement of carbon atoms. So this is some kind of micrograph of graphene. 0.14 angstrom distances. And this was originally fabricated by a Scotch tape approach, basically taking Scotch tape and putting it onto some graphite and peeling it off, and they were able to obtain a single layer of carbon atoms. Okay. Now they're that process is called exfoliation, and it's been much perfected. There's a whole industry to do this. For us, a graphene-type potential is obtained as follows. Let's look at the honeycomb structure over here. You could think of taking a bump function, say a smooth, real, rapidly decreasing atomic potential, and then putting it at each side. So in other words, we could sum over all of these translates. We sum over all the lattice vectors, and that gives a potential which satisfies the hypotheses of a definition of honeycomb lattice potential. What you have to do, though, is you have to pick x0 to be the center of one of these hexagons, and then it will satisfy all those properties. This is from a recent paper of Rexman, Segev, and others, where they studied the light propagation. This was an experimental paper where they studied the light propagation in honeycomb arrangements of waveguides. So this is the cartoon photo. If you look, you see this honeycomb arrangement of tubes. These are glass tubes, and light is injected light is injected in the z direction and travels down these tubes. This is how it looks like actually when you image the face of the device that they've made. So that's a honeycomb arrangement. Another thing that Segev and Chen and other groups do is something called optical graphene. What they'll do is they'll take a crystal, a photorefractive crystal, which has a nonlinear response to light, and they'll interfere beams. For a honeycomb lattice, it suffices to take 3 beams, and if you pick the angles of the beams appropriately, which corresponds to choosing the wave vectors appropriately, you can induce a very, very nice honeycomb, a 2-dimensional honeycomb structure, and then experiment with light propagating into the crystal at an orthogonal polarization. And the nice thing about this experimental system is just by changing the angles of the beam, you could deform the honeycomb structure. You don't have to physically stretch it the way with actual graphene. There isn't something like a damage threshold here. You could just look at that deform very, very easily. This process is called optical induction. So just to explain that a little further, let me introduce the dual lattice. So this is the original honeycomb, the original triangular lattice, and its dual is obtained by taking the dual vectors satisfying Vj KL is 2 pi delta JL. Okay, so these are the dual lattice vectors. So we have lattice, dual lattice. And in these nonlinear crystal problems, what they'll do is they'll take a superposition of plane waves, so this is the electric field, and they'll interfere them in a crystal whose dielectric response is such that the refractive index goes like the modulus squared of the input field. And if you choose the vectors R1, R2, R3, keeping in mind the dual lattice vectors of the honeycomb, you can generate a honeycomb lattice potential. This is what they do. Okay? And this satisfies all of the properties. Okay, so that's what a honeycomb structure is. And now let's talk about first some comments on the general theory of waves in periodic structures, and then specialize to honeycomb. So the spectral theory of Laplacian plus V, where V is periodic, is well developed. Here is so V1 and V2 are, well, for us, they'll be the honeycomb, the particular triangular lattice, but it could be more general. And to develop the theory of waves in such structures, one looks at the flow-K block eigenvalue problem. So for each K in the Brillouin zone, the Brillouin zone is a choice of fundamental period in the dual space. It's just the set of all points which are closer to the origin than they are to any other dual lattice point. Okay? So that's a regular hexagon for the honeycomb structure. So for each K is a vector, for each point in this two-dimensional set, one considers this family, this self-adjoint eigenvalue problem. This is sometimes called a pseudo-periodic or K pseudo-periodic eigenvalue problem. It depends on two parameters, K1 and K2. Well, K1, K2, not in the sense of these vectors, but just, I could call them Kx and Ky, or Kx1 and Kx2, the momentum components. K is sometimes called a quasi-momentum. Right? So equivalently, I could factor out this block phase and look for solutions of this periodic eigenvalue problem, also self-adjoint, where so now this amplitude Pxk satisfies this eigenvalue problem, where all I did was replace the gradient by gradient plus Ik. And this is for x varies in R2, K varies over the two-dimensional Brillouin zone. So being self-adjoint, for any fixed K, there is a discrete sequence of eigenvalues, mu1 of K, mu2 of K, etc. These are real numbers going to positive infinity. And they have corresponding eigenfunctions Pj, which are complete. For each K, they form a complete set of L2, periodic L2. All right, so here's a sort of a schematic. So the spectrum of the periodic potential then is obtained as follows. We have that sequence of eigenvalues, mu j, mu1, mu2, etc., and we look at the image of the Brillouin zone under those functions, mu j of k. Here's if I pick k equal to c, I get some point mu. This is, say, the jth band. As k varies over the Brillouin zone, I sweep out intervals. And those are the spectral bands. And in 2 dimensions, it was proved a long time ago by Dahlberg and Trubowitz that there are a finite number of gaps in the spectrum. 1, 2, 3 here. In 1 dimension, generically, there are infinitely many gaps, but in 2 dimensions or higher, there are only finitely many. And the spectrum is just the union of these images of the Brillouin zone. That's the L2 spectrum. Okay, so this is saying pretty much the same thing. We have the union of bands. And what we want to focus on is that not just these intervals, because the intervals are, not terribly interesting to look at. What's much more interesting are really these functions, these surfaces. Okay, these are sometimes called the dispersion surfaces. And what's important about them is seen if you just write down what the evolution operator is. The evolution, just by completeness of the block modes, you can represent the evolution operator as a direct integral, a sum over the bands. These are just a sum of Fourier integrals over the Brillouin zone. This is over that hexagon. And the mu b's are those dispersion functions. So it's the critical points, the singularities, the Hessians at critical points. It's the properties of these dispersions, of the dispersion surfaces that dictate the dynamics. Okay. So here's a typical picture that you'll see if you look up band dispersions, band structures. You take a periodic potential like this V of x. Here it's drawn as a square lattice, and here would be its Brillouin zone. And typically in numerics, what one does is look at some symmetry-reduced Brillouin zone, like this triangle, and then plots the eigenvalues, mu j, j equal to 1, 2, 3, as you move around the boundary of such a symmetry-reduced part of the Brillouin zone. And then you get curves. This is mu 1 as it varies around here, mu 2, mu 3, and sometimes you see gaps. And then you also see intersection points, and these intersection points are what I'm interested in. And it turns out for honeycomb structures, one can control where those points are. One can control the quasi-momentum, the k values, where these intersection points take place. That's what we're interested in. So just some further general comments. This is the spectrum from a one-dimensional periodic problem. There, the Brillouin zone is just an interval, say. And if I take a value k naught, a wave number where the gradient is not zero, then I get transport behavior of dynamics. Did I? Oh, okay, I didn't. Yeah. So here what I'm thinking of, let me just say, I'm taking initial conditions for the Schrodinger equation, psi x and 0, psi 0 of x, taken to be something of this type, say alpha 0 of delta x, e to the I k0 dot x. So if k0, so this is, so alpha 0 as a function of z is, say, a Schwartz class function, then this is what I mean by wave packet initial conditions, which are spectrally localized at k0. And if k0 is a place where the group velocity, the gradient, is non-zero, then one just gets transport behavior. And if k0 is located at a band edge, then the gradient is different from zero, but you can get dispersive dynamics on time scales on the appropriate time scales. Here, the time scale is going to be 1 over delta squared, and on the previous slide, time scales of order 1 over delta. Now, it turns out that these particular examples are not the only kind of behavior that you can get. So in general, it turns out that dispersion surfaces are not smooth. They're at best Lipschitz continuous. And that's a consequence of the min-max principle for eigenvalues. If you think of the periodic elliptic problem where we replace gradient by gradient plus ik, you can get the eigenvalues for that self-adjoint problem by looking at the Rayleigh quotient. And the Rayleigh quotient for each k is a nice smooth function of k. But now you're going to take mins and maxes over functions of smooth functions of k, and you'll get Lipschitz functions. So one could make that argument very precise that the eigenvalues are at best Lipschitz, are Lipschitz functions. And in fact, you do get conical singularities. You do get Lipschitz behavior. So what this is a picture of is the intersection of two surfaces. Now think of mu1 of k and mu2 of k, those dispersion surfaces plotted over the Brillouin zone. And this is plotted for what's called the tight binding model of graphene. So tight binding is a kind of difference operator approximation in the limit of infinitely deep potentials. And this is really, that's the workhorse of physicists who work in condensed matter physicists. Most of their modeling is based on the tight binding model. Okay, I'll say a little bit more about this later. And Dirac points arise when the points that we'll be interested in, Dirac points are points that arise from the touching of consecutive dispersion surfaces. There's a little gap there, but that's just numerical. In fact, we prove that generic structures do have these conical points. And such conical singularities are actually known even for Maxwell's equations with constant coefficients, but in anisotropic media. It goes back to, well, the prediction actually goes back to Hamilton's work and was studied mathematically by a number of authors after that. But this is a consequence of the vector character of polarization effects. So why are such Dirac points important? Dirac points are important because these conical intersections permit tuning of the physics. you have think of a fixed periodic structure giving you a conical singularity in its dispersion surfaces, and now deform the structure. If you deform it appropriately, you can actually open up a gap in the spectrum. If you open up a gap, right, so the eigenvalue is in the vertical direction. So if you see that there is a gap, then that's a place where there are no eigenvalues. There are no propagating modes. There's no propagation. So you have it like an insulating state. And if the gap closes up, you have something like a conducting state. So these so honeycomb structures are first of all important because they live on the design boundary. They're very tunable structures for electronics and optics. Now, this conical singularity sort of the dispersion surfaces suggests that there might be wave-like properties, like the wave equation, non-dispersive behavior. And in fact, here is some simulations from work of Ablowitz and Zhu, which show kind of Huygens principle behavior when you start with wave packets, which are spectrally concentrated at such momentum points. A second reason why these are important are the existence of topologically protected edge states. So in this picture, this is work done by Marin Soljacek and co-workers, where what they do is they take two structures which have one with a Dirac point, one with a conical singularity in its dispersion relation, and another structure which doesn't, and they interface them. So since there's an interface between two different structures, you expect surface waves. But the remarkable property of this interfacing of structures is that you can excite waves which propagate in only one direction. There's no back propagation. Even more remarkable is if you put an obstacle in the way. Notice that the energy is just propagating around the obstacle. There is still no backscatter. So you can engineer structures which allow for unidirectional propagation and are very, very stable to perturbations of the interface. These are sometimes called topologically protected states. There is an underlying integer invariant, actually, that classifies these. So the rest of the talk will be about the existence of such Dirac points. How do they come about for arbitrary structures, not necessarily small amplitude structures? And furthermore, the dynamics of wave packets and Dirac equations. And I'll refer to the nonlinear Schrodinger variant of that. So, Dirac points. So, here's the picture to keep in mind. So a Dirac point, we say that K is in the Brillouin zone, in that hexagon is a Dirac point, if in the neighborhood of the K, of that value of the quasi-momentum, there are two dispersion surfaces. There are two eigenvalues, which as you let the parameter K vary, intersect conically. This coefficient lambda, mod lambda, it should be strictly positive, and this is in the condensed matter literature. This is called the Fermi velocity. So the theorem that we prove is the following. So let's let V of x be a honeycomb potential, which is non-degenerate in this sense. This essentially excludes the zero potential, and consider the following family. We take V, which satisfies the properties of honeycomb potential, and let's look at Laplacian plus epsilon V, where epsilon is not necessarily small. And we show that for generic values that there are that there are Dirac points. There are conical intersections of consecutive dispersion surfaces. There are no assumptions on the size, and it turns out that at non-generic values of epsilon, there can be higher order band crossings, and so we can't exclude those by our methods, except for when epsilon is small. So a bit more precisely, there is a countable closed set, C tilde. So this is a bad set. If we're outside of this set, then we have Dirac points for minus Laplacian plus epsilon V. So think of this as a discrete set of points going off to infinity with possible accumulation at it. And we believe we can actually replace this set C tilde just by a discrete set with only accumulation at infinity with a more refined analysis. So here is precisely what we mean by a Dirac point. We have locally conical behavior. And there's this coefficient over here, lambda, a mod lambda, which has to be positive, and this is what we call which is called the Fermi velocity, something that has to be studied carefully. And it's a complex number, and we're interested in showing that this is non-zero. Remember, these are eigenvalues. These are consecutive eigenvalues of the flow K block eigenvalue problem, and so there's a degeneracy. When K is equal to K star, these agree with each other. The eigenspace associated with them has a certain structure to it. You can obtain one of the basis vectors of the eigenspace from the other by applying conjugation and inversion. Okay. Here's the expression for lambda for the quantity whose modulus is the Fermi velocity. It's a lattice sum over Fourier coefficients of these degenerate block modes. And a key part of the analysis is learning how to treat the variations with epsilon, because in general it's not analytic. For small epsilon, we could say a lot more. We can say that the intersections of the dispersion surfaces happen at either the first and second or second and third bands, but in general, we don't know which bands intersect. We can ask the question, when do Dirac points persist? How can I deform the honeycomb structure and have the persistence? So it turns out that if your perturbation, this is some operator, if it commutes with conjugation and inversion, then small perturbations in the appropriate operator norm will not destroy the honeycomb structure, although the cones, the conical points, will be located not necessarily at the vertices of the Brillouin zone. They'll move interior to the Brillouin zone. So what can happen is you can have two cones that move into the Brillouin zone, and eventually, if you shear the medium enough, they might intersect, and then eventually you'll get some kind of quadratic smooth structure with a gap. Here's a concrete example of a deformation. I could take a uniformly strained lattice. I could replace the potential V of x by V of mx, where m is a 2 by 2 real invertible matrix such that mm transpose minus the identity is small. This will induce a perturbation which, well, if this is small, the Dirac points will move. I'll still have conical behavior, but not located at the vertices of the Brillouin zone. Or I could perturb the potential appropriately, which would correspond to changing the angles of those interfering beams and deforming the lattice that way. If you break inversion symmetry or time reversal symmetry, if you break symmetry, then what happens is immediately, regardless of how small the perturbation, a local gap will open. So, well, okay, I won't spend time on that. Previous work, well, as I mentioned, the workhorse of condensed matter physics is the tight binding model, which actually goes back to 1947. Wallace wrote a paper called The Band Structure of Graphite. He was interested in three-dimensional graphite, and he wrote down the simplest possible model for which he could work out with honeycomb symmetry, such that he could work things out. So this was essentially a difference operator. He put in exponentials, and he obtained two bands which touch, as in the picture you saw before. And then there are various formal calculations, but our results are the first rigorous results for arbitrarily large epsilon that are generic. One can ask, well, what's the dynamics? Once we have the dispersion behavior, what is the dynamics of wave packets? So now a wave packet concentrated at a Dirac point, at one of those momentum points, excites a degenerate mode, right? Because the dimension of the dimension of the eigenspace is 2. So this is what a wave packet looks like. This factor of delta is just to keep the energy equal to 1. So that's a wave packet spectrally localized at a vertex k star. One could look for solutions of this type and then ask, well, what are the homogenized, what are the effective equations for the amplitudes? And we proved that on a very long time scale, those amplitudes evolved according to a 2-dimensional massless Dirac equation. So this is why in the condensed matter physics literature, people say that what you get in graphene are quasi-particles that are behave like fermions. It just means that if you look at wave packets, they behave according to a Dirac equation, which is a relativistic equation. And this is true on a very long time scale. If you deform the structure, you still get Dirac equations. You get something that's a bit more complicated looking, but it turns out that you can actually map them by a Galilean transformation back to the former type equation. So you get what are called tilted Dirac equations for deformed structures of this type, say if you make some kind of a uniform strain. And then in the nonlinear case, you get nonlinear Dirac equations. And these evolution equations are actually poorly understood. We know what it means for waves to for wave propagation in a focusing or defocusing medium for a nonlinear Schrodinger equation, but somehow the meaning of G, the meaning of focusing or defocusing, is unclear in these envelope equations. And so it would be very interesting if someone could tell me whether there's singularity formation for this, even in what corresponds to the defocusing case. This is a difficult problem analytically. It's L2 supercritical in the scaling sense. Okay. Well, with a little time, I'll just comment briefly on some of the ideas. So where do Dirac points come from? If you look at the Fourier analysis on the honeycomb structure, you first look at this Floquet operator, where you replace gradient by gradient plus ik. And you could say, well, all right, the Dirac points are located at the vertices. What are so special at about those quasi-momentum? So what is special about them is that if you look at this, operator, which just rotates the argument by 120 degrees, so Rf is just f of a rotated argument, then it's exactly at those vertices that this operator, that the Floquet operator commutes with this rotation. And because the rotation has eigenvalues, rotation by 120 degrees has eigenvalues 1, tau, and tau bar, you can break L2. The space of L2, L2k are the L2 functions which are k star quasi-periodic. You can break that into an orthogonal sum in each of those eigenspaces. And that means you can reduce the problem of looking for degenerate eigenvalues to the one of looking for simple eigenvalues, which is a much more tractable analytical problem. So we could study 3 separate eigenvalue problems. This is what a Fourier series looks like on the honeycomb structure in each of those summands. So these are the coefficients that you saw in the Fermi velocity. And this is a sum over, well, the rotation induces 3 cycles, and so you have to take one representative from each 3 cycle, and that's this set S, which is a subset of Z2. So this is the natural Fourier language for the honeycomb structure. And to detect a Dirac point, what we have to check is the following, that so K star is a Dirac point now if there is a degenerate eigenvalue with a certain structure to its eigenspace. The eigenspace should be the direct sum of an L2k tau eigenvalue and L2k tau bar eigenvalue, and you have to make sure that it's not a triple eigenvalue. There should be something in the one eigenspace of the rotation. And then finally, this has to be true, this non-degeneracy condition, which says that the cone actually opens. So these guarantee that there is a vertex of the cone, and this tells you that the cone actually opens, and you get a Dirac point. How am I doing with time? Okay. So the idea is a continuation argument. We'll continue from epsilon equal to 0. If epsilon is equal to 0, so here I'm interested in studying h of k, which is minus gradient plus ik, say k star, which is, k star is some point, some momentum. This is k space. This is k star. So I'm interested in studying this operator. And here is going to be epsilon, my continuation parameter. And here is mu. Let's call it mu of k star. And it's going to depend on epsilon. So when epsilon is equal to 0, simple geometry tells us that there is a triple eigenvalue of the Laplacian. So this is the free problem. It's just Laplacian u is equal to mu u. And the fact that this rotation matrix just preserves length, and this particular geometry of the hexagon gives us that there is a triple eigenvalue. Now, you could check perturbatively that that triple eigenvalue splits into a double eigenvalue and a single eigenvalue. So this eigenspace over here is L2k star 1, and this all along here is a double eigenvalue, which looks like L2k star tau direct sum L2k star tau bar. Okay. And we want to show that that picture persists. I want to show that this curve, you continue to get double eigenvalues with that structure. So this is the small epsilon expansion. Well, you see how far you can go. You try to proceed by continuation. You let epsilon c be the supremum over all values of epsilon, such that the hypotheses which ensure that you have a Dirac point hold. And, well, as a function of epsilon, these are Lipschitz. So if there's a finite value where you stop, then you know that that eigenvalue has to be finite. Right? If this were infinity, then I'd be done. Then I would know that I get a honeycomb structure all the way up to infinity. So one needs a way, in order to do the continuation at an arbitrary epsilon, one needs some kind of an analytical characterization of these eigenvalues. And we proceed by writing down a Lippmann-Schwinger type equation. And so eigenvalues are going to be characterized by something like a characteristic polynomial, and the natural thing to do is to take the determinant of this operator. It turns out, though, that because one's in 2 dimensions, the operator determinant isn't defined because the operator isn't trace class. However, its square is trace class. So it's possible to introduce a renormalized or a regularized determinant. The idea is just this. Instead of working with identity plus t, work with e to the minus t times identity plus t, because this is identity minus t, and identity minus t times identity plus t is identity minus t squared. So that's the idea. And that's what this det 2 is. So we form that determinant, that regularized determinant in each of the eigen subspaces, sigma equal to 1, or sigma tau bar. And we have to check that, we have to look for zeros of E sub tau, and we want to make sure that E sub 1 is non-zero. So we need zeros of this quantity to be non-zero, and we also need for the cone to open, so we need for the Fermi velocity to be non-zero. And if these hold, then we have this kind of local character of the dispersion surface. And so I'll just conclude with just a comment on an interesting technical aspect. We have to look for zeros of this function, and then we want each of these factors to be non-zero, so we look at their product. And we'd like to use a kind of complex analysis continuation lemma. But there's a serious technical point involved. The Fermi velocity is a function of the Fourier coefficients. It's essentially a function of an infinite vector. And that infinite vector depends on parameters in the problem. And as we vary those parameters, even though those parameters appear analytically in the equation, the eigenvector, this choice of eigenvector might not vary analytically. Although the eigenspace might vary nicely, there might not be an analytic choice of eigenvector. So that's what the obstruction is. And so we have to find some way to get around that obstruction, what's essentially a topological obstruction. So what we do is we look at a Lyapunov-Schmidt reduction of the eigenvalue problem and reduce and take a large finite dimensional approximation of it. Okay, so there is some large matrix approximation, and we apply the following linear algebra lemma that I'll conclude with. So we're looking at a simple eigenvalue of an m by m matrix, where m is a very, very large number. It depends on epsilon. It could be growing very, very rapidly with epsilon, but we fix epsilon. We look at an m by m matrix approximation, which that matrix has rank m minus 1. And as parameters vary, that is, the entries of the matrix vary, we would like to have some kind of an analytic choice of eigenvector, and you can't do that even for 2 by 2 complex matrices. But what we find is that there is a map from the space of rank m minus 1 matrices with the following property. So we can write down a list of functions, which are polynomial in the entries, actually, with the property that each of these functions is an eigenvector, and one of them is non-zero. As you vary the parameters, there's always one which is non-zero. And what this corresponds to is the following fact. If I look at a rank m minus 1 matrix, I know that the determinant is 0. That means that one of the since it has rank m minus 1, that means that there is one subdeterminant which is non-zero. One m minus 1 by m minus 1 subdeterminant which is non-zero. But I don't know which one is non-zero as I vary the parameters. And that's the origin of the topological obstruction. So when we have to write down, in other words, we instead of writing down this object, we have to write down a vectorized version of this, which is analytic, and if it's non-zero, then that's enough for us to do the continuation. So I'll just summarize. Well, we talked about scattering and microstructures, and the questions forward are looking at the two-dimensional edge bifurcation. We believe that there is a localization and dispersive estimate associated with that, and that there is no such effect in 3 dimensions or more. And then we talked about Dirac points and Dirac-type dynamics, and the work going forward with Charlie and with a student of mine, James Lee Thorpe, is on topologically protected edge states. So I'll stop there.
Questions? Okay, I'd like to ask one myself, if I may. The honeycomb is a particular multi-lattice in 2 dimensions. Mm-hmm. Does this analysis suggest other multi-lattices in 2 or 3 dimensions that might also have interesting properties?
There are interesting examples in 3 dimensions that with what are called Weil points. These are sort of occur more frequently than Dirac points, but there are quite a number of such examples. I'm not familiar with their details, but yes, there are problems with degeneracy with such structures. We're hoping that these methods will apply, but I don't have particular examples under control just yet. Yeah.
Any other questions?
Yeah.
Along those lines, my understanding was that graphene is a wiggly 2-dimensional structure. So would that affect the results at all?
Yeah, there is a kind of wrinkling that's known for graphene, and I think an interesting question would be to see what are the wave properties, what are the curvature-induced effects for things? Do you gap structures in that way? I think that things would have to wrinkle globally to open up a gap, because if you make sort of a compact perturbation of such a structure, if the distortion is purely local, then you would expect only to add eigenvalues to the spectrum. You wouldn't expect it to pull open a gap, but yeah, the wrinkling is quite interesting. Happens when you put it on a substrate, the way it's grown. Yeah.
You mentioned Dirac equations as models for graphene sheets also. Could you comment on the difference between, or why one point of view would be more interesting than the others? It is a model with using Dirac equations or using a Schrodinger type description?
Well, so the behavior is truly Dirac in the neighborhood of these conical singularities. So once you deform sufficiently or deform in the, if you break time or inversion symmetry, then you'll get, once you gap the structure, once you create a gap in the structure, perhaps I should have drawn this, so you're going from a structure which looks like this to one like this. So this is, if you, so either you could do this by a large deformation with time reversal and inversion symmetry, or you can achieve this by even a small deformation where you break, either one of these. Here the behavior would be Schrodinger dynamics, right? And here you would always get Dirac dynamics. So the Schrodinger dynamics, there if you look at the wavefronts, they'll be very, very dispersed, very diffused, whereas here it's a bit like dropping a petal in a pond. You would just see a kind of a sharp Huygens principle, or actually the behavior corresponding to the two-dimensional wave equation, but it is a vector character.
Okay, thank you very much.
Okay, thank you.